So yeah, let's kind of refresh our memories a little bit on what we were talking about last time. So it's definitely true that the derivative of the natural log of x is equal to 1 over x. And we came to see last time that if you take the antiderivative of 1 over x, you don't just get the natural log of x, you actually get the natural log of the absolute value of x plus c. And to expand upon that a little bit, if we take the antiderivative of 1 over some u du, we're going to get the natural log of the absolute value of u plus c, which is kind of leading us towards this idea of a nice U substitution. So for example, if I want to take the antiderivative of, say, 1 over x plus 4 dx, I'm going to either do it the long way, which is totally fine, where we're going to let u equal the denominator, right? That's only kind of the only real plausible choice for you. So we let u equal x plus 4. Our du is going to be 1 times dx. And if we rewrite the integral, we're going to have the integral of 1 over u du, which we exactly just said was going to equal, oh, sorry, I think someone just wrote something in the chat, the natural log of the absolute value of u. I should make this bigger. Yeah, cool. And then that's going to end up being the natural log of the absolute value of x plus 4. But we talked a lot last time about how you could do this kind of as a mini U substitution, where you don't really have to do the U sub. You'd be like, well, I've got 1 over some stuff. As long as that stuff is just a, how do I say this the right way? As long as that stuff is just a linear function of x, meaning you've got some multiple of just x plus some constant. You can kind of go straight to saying, well, I'm pretty sure that the antiderivative of 1 over x plus 4 is going to be the natural log of the absolute value of x plus 4. And for me, I would do a mental check. If I take the derivative of that, what do I get? Oh, I get 1 over x plus 4. When you take the derivative of this, you should really kind of just ignore the absolute values, to be perfectly honest. Like think about taking that derivative and just be like, absolute value, not there. But then we can extend this to the idea of something like the antiderivative of 1 over 2x plus 5. We could do it the long way, where we let u equal 2x plus 5. Our du is 2 times dx, and then 1/2 du is equal to dx. So that when we take the integral of this, it becomes the integral of 1 over u times 1/2 du. And then the 1/2 is a constant that just sticks around. So we get 1/2 times the natural log of the absolute value of u plus c, which is 1/2 the natural log of the absolute value of 2x plus 5 plus c. But I don't want you to do it that way. I mean, that's not true. I want you to do it whatever way works best for you, but I want for you to be able to do it without having to write all that. So instead we can be like, well, I'm pretty sure that looks like 1 over some linear function of x. And that's going to be probably the natural log of the absolute value of 2x plus 5. But the problem with that is, if we check it, if we take the derivative of the natural log of 2x plus 5, we get 1 over 2x plus 5 times 2. Welcome. Thanks. So to account for that 2 that's going to be there, we of course need a 1/2 out in front here, or a division by 2, whichever way you want to say it. So that's the way I would encourage you to think about these mini U substitutions, is you're undoing the eventual multiplication by a constant. So I would encourage everyone to quickly do this next problem on their own, and I'll give you a minute. I always try. It's always a challenge here. So if you're watching the video later, pause it, give yourself a moment to do this following interval. Find the antiderivative of 1 over 3x minus 7. So it's going to end up being the natural log of the absolute value of 3x minus 7. But then I need to, what do I need to multiply by to make that right? 1 over, yeah. And we need a plus c. There's our antiderivative. Ooh, that's a little blurry. Okay. I think it's when I like shake the table. Well, maybe not. Well, it just seems to happen sometimes. So we can totally make a rule. This will always work. But the antiderivative of 1 over ax plus b is going to equal the natural log of ax, of the absolute value of ax plus b. And then we need to multiply by 1 over a to account for that eventual multiplication. Plus c. So we could do a couple more. For example, what's the antiderivative of 1 over 9 minus 5x? This one often, this little extra piece here often trips people up. I know I'm going to get the natural log of the absolute value of 9 minus 5x. And sometimes people want to say, I'm going to do multiplication by 1/5, but it's actually a 1 over negative 5 or a negative 1/5. We need to account for that. So I need the negative 1/5 out here. If you're ever unsure, you can always check. So if we want to check it, we're like, okay, well, the derivative of negative 1/5 times the natural log of, again, I would encourage you when you're taking the derivative of this to just kind of ignore the absolute values. Take the derivative of that, it's going to be negative 1/5 times 1 over your stuff times the derivative of that stuff, which is exactly a negative 5. And that negative 5 will cancel out the negative 1/5. You might observe that I didn't write the plus c when I was taking the derivative, because I know when I take the derivative of a plus a constant, that derivative is just going to be 0. You could write it in there if you really want to. It doesn't really change anything. Just don't write it in there. And so this will work kind of for anything where the denominator is a linear function of x. So one more example. In fact, why don't you all try this one? Let's find the antiderivative of 8 over 0.5x plus 6 dx. Oh. When you have a moment, let me see your symptom survey. For those of you joining us, there's the attendance form. So you don't have to do this first step, but I often, when I have a constant multiple, I like to pull that out in front. So I would rewrite this as 8 times the integral of 1 over 0.5x plus 6. Not necessary, but it might make it easier to see what to do. And then we're going to say, well, that's going to be 8 times the natural log of the absolute value of 0.5x plus 6. And then I'm going to divide by 0. Now, maybe it's easier if I write that as a fraction. Instead of dividing by 0.5, maybe it'd be easier to think about if I was dividing by 1/2. But really, dividing by 1/2 is the same as multiplying by the reciprocal. Thank you. So that's going to equal 8 times 2 times the natural log of the absolute value of 1/2 x plus 6 plus c. So we're getting 16 times the natural log of 1/2 x plus 6 plus c. So especially when I know I'm going to be dividing by something, dividing by a decimal is never nice, but if you write it as a fraction, then you can just multiply by its reciprocal, and that's usually pretty not too terrible. All right, sometimes things look like maybe they should be have an antiderivative that's a logarithm, and they're not. For example, what if we wanted to find the antiderivative of, let's say, I'm trying to kind of number things here. A few students gave me some feedback that it would be nice if things were numbered so we keep track of them. So I'm going to try and do that. What if I want to take the antiderivative of 1 over 5x plus 2 quantity squared dx? And so what I really want to point out is this is not going to be equal to the natural log of the absolute value of 5x plus 2 squared times 1/5. Definitely not. How do I know? Well, let's check. If we take the derivative of this, the derivative of 1/5 natural log of 5x plus 2 squared, if I do my logarithm rules, it's going to be 1/5 times 1 over the stuff times the derivative of the stuff. And the derivative of 5x plus 2 squared is 2 times 5x plus 2 times 5. And one of those 5x plus 2's cancels, and the 5's cancel. And we're left with 2 over 5x plus 2. Definitely not what we need it to be. So I really want to stress that when you're finding a antiderivative and we think it might be logarithmic, we usually think it might be logarithmic because you have 1 over a linear function of x. And that denominator there is not a linear function of x. It's actually a quadratic function of x. So we need to do something different. In fact, here is a great time to do a U substitution. So u equal 5x plus 2, and our du is 5 dx. So 1/5 du is just dx. So rewriting the integral, we're going to get the integral of 1 over u squared times 1/5 du. Totally not a logarithmic integral. So that's going to be 1/5 times the integral of u to the negative second. And then we're just going to use the reverse power rule. So we're going to get 1/5 times u to the negative first over -1. Let's see. And then we're going to plug back in. I would probably rewrite this before I plug back in what u is. I would probably rewrite this as -1/5 times 1 over u. Let's see. To me, that just feels nicer. And then I would plug back in and then get -1/5 times 1 over 5x plus 2. Let's see. Let's look at where did I write? I wrote down a question. This is the time to do it. Where'd you go? I disappeared. Sorry. I hide that from myself so well. Good job. 1 second. I have a question. What I thought was a really good question. It's hiding from me. There we go. I found it. Okay. No, okay. Little James. I feel like I'm losing my mind. Oh, well, I've got other examples that are very similar. So let's try this one. So we're going to do the integral. Let's keep the numbering. 7 of x plus 4 over x squared plus 8x plus 1 dx. So now things are getting a little trickier. When we're faced with integration, currently we kind of only have a couple things we can do. We can either simplify it. It can't really simplify that, right? There's no nice way of like making that look different, really. Or we can try a U sub. And again, back to what kind of ways we choose our U's. You want to pick something that's stuck, and you're hoping that the thing you pick has its derivative also in the integral. Those are the two kind of ways we're picking a choice for U. So what seems like a reasonable choice for you? It looks like x squared plus 8x plus 1 seems real reasonable, because if we take the derivative is 2x plus 8. And while I don't exactly have that, I do have a multiple of that, right? I could divide both sides by 2 or multiply both sides by 1/2 and say, or even easier, just factor out the 2. du is going to be 2 times x plus 4 times dx, which is good because I have exactly an x plus 4 times dx. So I can say that 1/2 du equals x plus 4 times dx. So this part here is going to be my 1/2 du. And so my integral is going to become the integral of 1/2 du over u. Or as I would probably prefer to write it, 1/2 the integral of 1 over u. Either way of writing it's fine. I find it easier to see what I'm supposed to do if I write it this way. So we're going to get 1/2 natural log of the absolute value of u plus c, and then that's going to be 1/2 natural log of the absolute value of x squared plus 8x plus 1 plus c. Questions about this one? Those of you on Zoom, also welcome to ask questions. Here's the attendance form again in case you have anything you need to fill out. Let's look at something that looks very similar but is very different. Let's look at the integral of x squared plus 8x plus 1 over x plus 4. And what I really want to stress here is we can't do a U substitution here. If you try making the same choice, if you were to try letting u equal x squared plus 8x plus 1 and getting du equal to 2 times x plus 4 dx, what I really can't stress enough is we don't have an x plus 4 times dx in this integral. We have a 1 over x plus 4 times dx, which is a totally different thing. So if you try to do 1/2 du equals x plus 4 times dx, we have to recognize, oh, we don't have this. So we can't make this U substitution work. So typically, when you're picking u to be a thing, du has to be a thing that's in the numerator. Or that's not exact. That's it. You can't have the reciprocal of what you want. There's other examples where the thing that you want is in the numerator because like it should be there. But in this case, we really want x plus 4 in the numerator and it's not. So instead, we have to do something else. And here's another way you can simplify integrals, specifically integrals where you have a rational function. We can do polynomial division if the degree on top is greater than or equal to the degree of the bottom. So if the degree on top is bigger than or equal to the degree on the bottom and nothing else seems good, one thing we typically want to try is polynomial division. So we're going to divide x squared plus 8x plus 1 divided by x plus 4. So then we ask ourselves, okay, what do you multiply by x to get x squared? And the answer is x. And then you multiply x times x is x squared, x times 4 is 4x. Funny, I was helping someone with a problem like this yesterday, and they did this thing where they automatically switch the signs. Like I've never seen someone, like some people like to do this thing where they switch the signs. I never has worked for me that way. I'm always just thinking I'm subtracting, and then x squared minus x squared is 0, and 8x minus 4x is 4x. I feel like I have to sneeze. Okay, bring down the 1 and then do the whole process again. What do you multiply by x to get 4x? 4. 4 times x is 4x. 4 times 4 is 16. Subtract. 4x minus 4x is 0. That's why we picked 4 in the first place. And 1 minus 16 is negative 15. So doing this polynomial division allows us to rewrite the integral, because we can now say, oh, this integral is equal to the integral of the quotient, which is x plus 4, plus the remainder, which is negative 15, divided by the denominator, which is also x plus 4. This is not a good example in that the numerator, the divisor and the quotient happen to be the same. That's atypical, right? So I should really stress this x plus 4 is going here, and this x plus 4 is going here. We'll do another example where it's not so coincidentally the same thing. So then we can integrate this. The antiderivative of x is x squared over 2. The antiderivative of 4 is 4x. And the antiderivative of negative 15 over x plus 4 is minus 15 times the natural log of the absolute value of x plus 4. So again, I'll repeat. If you have a rational function, meaning the top is a polynomial and the bottom is a polynomial, if the degree on the top is bigger than or equal to the degree on the bottom, we can do polynomial division. In fact, it's usually one of your go-tos, unless there's a really, really obvious U substitution that makes sense. It's kind of like we should try polynomial division if we can. So I would like all of you to try the next one, which I wish I could find the one I've written down, but oh well, it's lost forever and ever. It'll probably show up later. I'm like, oh, there it is. I want you all to try this one. Try the integral. Let's see how. I should be careful here. Sure. Let's try 3x squared plus 5x plus 1 divided by x minus 2x. And then we'll tell you right from the get-go, you want to do polynomial division, right? There isn't something else to do. So start with this. Do that. I'm going to look for my hidden problem today. Yeah. Yeah, totally. Yeah. Okay. Sure. Well, so after this one, yeah, we'll do that. So you guys work on this for a minute while I look for something. Came in and I wrote a thing down. Like, did it for myself really well, apparently. So let's take a look. whenever you're doing this polynomial division, you're always looking at like the highest power things, meaning in the x minus 2, I'm looking at the x, not the minus 2. The minus 2 is just kind of along for the ride. And over here, I'm just looking at the 3x squared to start. So I'm asking myself, you can either ask how many times does x go into 3x squared, but I feel like the better way of phrasing that question is, what do you multiply by x to get 3x squared? And the answer is 3x. And then we do the multiplication. 3x times x is 3x squared. 3x times minus 2 is minus 6x. And then we subtract. I like doing it like that, but people often just like change the signs. Add also works just fine. Just make sure you're careful, especially when it's negative here. It's easy to mess up the addition or subtraction. So that's 0. You don't really need to write that. And then 5x minus 6x is 5x plus 6x, which is 11x. Bring down the next term, wash, rinse, repeat. What do you multiply by x to get 11x? The answer is 11. 11 times x minus 2 is 11x minus 22. Subtract, that's a 0x, and 1 minus 22 is 23. So then we have to rewrite the integral as the integral of the quotient, 3x plus 11, plus the remainder divided by the divisor. These are equal to each other, right? Because when what you're saying is this divided by x minus 2 is equal to 3x plus 11, plus a remainder of 23 that still needs to be divided by x minus 2, which is why we get this part over here. And if you wanted, you could totally multiply this by x minus 2 over x minus 2 and get back to there. You shouldn't, but you can. So then the rest of this is just anti-differentiation. We're going to get 3x squared over 2 plus 11x plus 23 times the natural log of the absolute value of x minus 2 plus c. Number 9. Questions about this one? Yeah.
Can you repeat the last step, like from the second to last step?
Like from here to here?
Yeah, for the 3x squared.
Sure. So what I'm using is the reverse power rule. So we have this rule, just a reminder, right? We know that the antiderivative of x to some power is equal to x to that power plus 1 divided by the new power. So that's what I'm using here. So here, my power is 1, and I'm adding 1 to that power divided by the new power. And I'm technically using that rule here, although really I'm just saying we know that the antiderivative of a constant is the constant times x. Because the derivative of 11x would be 11. Cool. Let me do, so you said you had a question in a similar vein? Cool. What is it? Sure. Let's take a look. Right. All right, so we can take a look at that, but I feel like we need a little more, we need to say a few things before we go quite here. But yes. I'll write that down. So, yeah, let me write that down over here. So have your classes started talking about definite integrals? Because that's definitely what that question is talking about, as a definite integral. So has your teacher started talking about that? Okay. So we can start moving. So I guess we can start talking about definite integrals, but here's the issue. There's kind of a lot of machinery that builds up what the meaning of a definite integral actually is. But the actual execution of how to calculate a definite integral is pretty straightforward. So we can talk about the calculation of definite integrals, and then next class maybe talk more about like what the meaning is, where that's all really coming from. So the difference between an integral and a definite integral is whether or not you have limits of integration. So an indefinite integral is what we've been doing so far. So an example of an indefinite integral is literally any of the integrals we've done. So it's just a fancy word or fancy phrase for an antiderivative. So for example, if I said find the indefinite integral there's no from, of e to the 3x dx, your answer would be the function 1/3 e to the 3x plus. And again, that's another example of a mini U substitution where we're not actually doing the U sub. We're just like, oh yeah, I know if I take the derivative, I have to multiply by 3. So the antiderivative, I'm going to need to divide by 3. And what I really want to emphasize here is that when you're doing an indefinite integral, the answer is a function. On the other hand, definite integral which I encourage you to think of as an area, because that's actually one of there are many interpretations of what, just like with a derivative, there are many interpretations of what it means. One way we think of a derivative is like the slope of the tangent line, or you can think of it as velocity if you know position. Very, very generally, it's a rate of change. It's how one thing is changing as another thing is changing. Well, in a very, very similar way, definite integrals have many interpretations. The most common one being the area under the curve, but there are lots of other ways of thinking about it. Like if you know velocity, it can give you position, or if you know acceleration, it can give you velocity. It takes you kind of back up to the previous function. But an example of this would be something like the integral from 1 to 3 of 3x squared dx. And so when you do something like this, the process is going to be to find the antiderivative. The antiderivative of 3x squared is x cubed. And then you're going to evaluate that function between the lower limit 1 and the upper limit 3. Which means, all this notation means is you're going to first plug in 3, you're going to subtract, and then plug in 1. So you're going to end up getting 27 minus 1, which is 26. I don't care, well, not that I don't care. I don't want you to focus so much on the calculation of this right this moment. What I want you to focus on here is that when you find a definite integral, the answer is a number, not a function, right? You're getting some actual number that is representative of how much area is under the curve. So, yeah, there's a whole kind of lot. Yeah, question. No, so for example, someone might ask you, someone might give you a question like, find the area under the curve y equal to 1 over x between x equal to 2 and x equal to 10. They might rattle those words, or they might just say equivalently, calculate the following. These two things mean the same thing. And graphically, they're saying, okay, here's your curve 1 over x. And they're saying, okay, from x equals 2 to x equals 10, they're asking the question, how much area is there right there? Yeah.
So if it's then it's asking area, it's like
Correct. Well, so here's the thing, and this is kind of getting at the root of everything here. This is literally what calculus is all about, because we're really kind of circling around something called the fundamental theorem of calculus, which is that the way we calculate the area under the curve is by finding the antiderivative of the function that we're trying to find the area under, and then substituting in the limits of integration. So someone could ask you to calculate this. And the way we're going to calculate it is by finding what's the antiderivative of 1 over x. We've done it a few times. Yeah, natural log of the absolute value of x. Which you don't actually need here because all your x values are positive, but it's still good to be very precise. And then we would evaluate that between 2 and 10. So to answer your question again, is Devin? That's what I'm saying right? Okay. To answer your question again, they wouldn't give you this. We'd be expected to come up with this. And then also plug in. Now, whenever you're plugging in, it's always the top thing first minus the bottom thing second. So that's going to be the natural log of 10 minus the natural log of 2. I dropped the absolute values because the absolute value of 10 is 10. The absolute value of 2 is 2. And then if I were going to do this, I would probably take one step further and simplify this, because we have a log minus another log. You can write this as the natural log of 10 divided by 2, which would be the natural log of 5. That would be my answer. No, you're good.
Is there any other way that this can be written? Because when in my practice midterm, it just says like integrals and it's mixed with like.
So both of these are referred to as integrals, both a definite integral like this and an indefinite integral like this. I could write that down and say compute that integral. And what I mean there is find the antiderivative. I could write this down and say compute that integral. And what I mean there is find the area under the curve. So unfortunately, no, there's not really a good way of, I mean, the way of differentiating between them is one of them has numbers at the bottom and top of the integral symbol, which means, oh, they're asking for us for an area under a curve. Whereas when you don't have numbers at the bottom and the top, it means they're asking you for the function that is the antiderivative of this function. But both of them, almost all the time, both of them require you to find the antiderivative. It's just that for the definite integral, you have to take the additional steps of plugging in your top limit and subtracting and plugging in your bottom limit. If we were going to do this one, oh, that's a good problem. E to the 1 over x squared over x cubed. I'm looking for a U substitution to do here. So I'm thinking, what am I thinking? Well, what seems like a possible candidate? Where do I usually want to pick U from? Yeah, so x cubed might be a good choice. X cubed is definitely stuck. But what's the derivative of x cubed? Yeah. And the problem with this choice is I don't have an x squared multiplied by dx, because the only x squared I have is in the exponent up there. So that leads me to saying, oh, that x squared that I wish was the thing x multiplied by dx, that 1 over x squared is also stuck, right? It's in that exponent. I can't get it out. So this seems less likely. I might move on to saying, well, what if I tried u equal to 1 over x squared, which you might prefer to write as x to the minus 2. Then our du is minus 2 times x to the minus 3rd. And that's looking good. Oh, sorry, don't forget the dx. The dx is super important there. If I divide both sides by negative 2, I have a negative 1/2 du equal to x to the negative 3rd is the same as 1 over x cubed dx. Yeah. So when I'm finding du, what am I actually finding? It's a good question. So when I'm finding du, what am I actually finding? Yeah, I'm finding the derivative of whatever u is. So I'm often, when I'm finding du, taking a little shortcut, meaning when it, all right, so real quick. So right, when I'm like in this problem, when I set u equal to x to the negative second, 1 over x squared, what I'm really doing is I'm taking the derivative du dx, and then the derivative of this is minus 2x to the minus third, and then I'm automatically bringing the dx over. So I'm kind of skipping that step where I'm writing the derivative, and then I'm moving straight to saying, oh, du equals this. But it's really, really good to remember that when you're finding du, you're just finding the derivative of u, and then you're multiplying it by dx. And then I'm trying to make this look like what I have here. And oh, look, I have a 1 over x cubed times dx. So I'm going to rewrite this as the integral of, well, my 1 over x cubed times dx is equal to negative 1/2 du. And then I am left with an e to the u. The integral of e to the u is e to the u. So I'm going to get negative 1/2 e to the u plus c. And then that's going to equal negative 1/2 e to the 1 over x squared plus c. And again, I'll remind you, this question asking us for the integral of e to the 1 over x squared over x cubed dx, the answer is a function because it was an indefinite integral. There are no limits of integration to plug in. Yeah. Exactly. In fact, let's do an example where we talk about that because it's something that's easy to see why you do it once you do it. So let's say I wanted to find the definite integral from, let's see, I'm trying to not be too crazy here. Sure. From 1 to 3 of, we can do that. Yeah, let's do that. Let's do 2x plus 1 dx. So you could throw in a plus c. But here's what happens if you do. So if I anti-differentiate 2x plus 1, it's going to be x squared plus x. And let's say I wanted to throw in a plus c just for the fun of it. Well, then we're going to evaluate this between 1 and 3. And if we do that, look what happens. When we plug in 3, what do we get? I'm going to get 3 squared plus 3 plus c. Minus, when I plug in 1, 1 squared plus 1 plus c. And what's going to happen to the c's? Yeah. So that's why we're allowed to completely ignore the idea of adding on a constant when it's a definite integral, because they're always just going to cancel out when we do the subtraction. So this is going to end up equaling 9 plus 3 minus 2, which is going to be 10. Now, the reason why I picked kind of a very, very basic example here where the function's right, just linear, is because we can actually see that this area is what it is without doing a definite integral. If I actually draw this, this function y equals 2x plus 1, I can do a decent enough job of drawing that. So let's see, my y-intercept would be 1, and then when I plug in 1, I would get 2 plus 1 is 3, and then I go, my slope is 2, so then 5, and then 7. Oops, close enough, right? Okay. So that's the point 3, 7. There's the point 1, 3. And I want to find the area under this curve from 1 to 3. Okay, well, that's a shape I know how to find the area of. There is a formula for trapezoids. Whatever. I'm going to make it easy and make it a triangle and a rectangle, right? Okay, trapezoid formula is not that bad. It's the base times the average of the heights. So this height is 7, this height is 3. The average of those two numbers is 5, and the area would be the base times the height. But it's much easier just to make it a triangle and a rectangle. So let's see. The rectangle has an area that's the base, which is 2, times the height, which is 3. So 6. And the triangle has an area with the base, or 1/2 the base times the height, which is, let's see, from 3 to 7, the height's 4. So 1/2 base times height, that's going to be just 4. And then adding them together, the total area is going to be 6 plus 4, which is 10. So the point of this example is the thing works, right? The area actually is 10 if you look at just using some geometry formulas, but we can also do it in this other way where you take the antiderivative and then plug in the limits of integration. Let's see what we have time. Okay. So let's see. A couple other things I want to say. Yeah, okay, so let's do. So it gets a little more interesting if you're limited, if you have to do a U substitution with a definite interval. And there's kind of 2 ways to handle that. Now I know we're kind of putting, as old people say, we're putting the cart before the horse. We're kind of getting ahead of where we might need to be because there's some stuff back here. But let's do one example and then we'll kind of circle back around. So let's say I wanted to do the integral of, let's make it not too terrible. Sure. Let's say we have x times the square root of x squared. No, x. So I'm going to change a little bit. X squared times the square root of x cubed plus 1 from 0 to 2. Got stop number. Number 12. Okay, so there are 2 ways you can kind of approach dealing with a definite integral along with a U substitution. We're going to do the U substitution first. So we're definitely going to let U equal x cubed plus 1 because our du is going to be something that works. Our derivative of x cubed is 3x squared, so our du is 3x squared dx. And then I'm going to adjust and say 1/3 du equals x squared dx. Okay, there are 2 ways of dealing with U substitution along with a definite integral. One way is to completely ignore the limits of integration until the very end. So what I'm going to do is I'm just going to say, well, I'm going to rewrite the indefinite integral. So the integral of x squared times the square root of x cubed plus 1 dx. That's going to equal, well, my x squared dx. I'm going to replace that with a 1/3 du. So this is going to equal the integral of 1/3 du. And then the square root of x cubed plus 1 is going to be the square root of u, which I should really write as u to the 1/2. Square root of u to the 1/2, same thing. But we know it's going to be easier to anti-differentiate as we write it, if we write it as a power. And then we're going to say that's 1/3 times u to the 3/2 divided by 3/2 is the same as multiplying by 2/3. I'm not going to write a plus c, not because there wouldn't be one for an indefinite integral, but this indefinite integral is just kind of like some side work I'm doing for myself to help me do the definite integral. So we don't really need to write the plus c. That's going to be equaling 2/9 times, if I plug back in what u is equal to, I get x cubed plus 1 to the 3/2. So then I can rewrite my definite integral in the following way. The integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. I just found the antiderivative of that. It's 2/9 times x cubed plus 1 to the 3/2. This is going to be 2/9 times x cubed plus 1 to 3/2 evaluated from 0 to 2. I will point out this is not my preferred way of doing it. I have another way of doing it, which I think is less kind of all over the place. But this is also perfectly fine. And then we plug in the 2. We get 2/9 times 2 cubed plus 1 to the 3/2 minus we plug in the 0. And we get 2/9 times 0 cubed plus 1 to the 3/2. This does simplify decently well. 2 cubed is 8, 8 plus 1 is 9, and 9 to the 3/2 power is the square root of 9, which is 3, cubed, which is 27. So 9 to the 3/2 is 27. And then we get minus 2/9 times 0 plus 1 is 1, and 1 to any power is 1. So I would factor out the 2/9 and say, oh, that's 2/9 times 27 minus 1, which is 26. So I end up with 52 over 9. Another way of tackling this is to do what's called changing the limits of integration. So when we do a U substitution, we're changing the integral to being in terms of U instead of in terms of X. Well, you can change your limits of integration as well, because these are supposed to be from x equals 0 to x equals 2. So we can say, well, if I do my integral from 0 to 2, x squared, square root of x cubed plus 1 dx. I'm going to make the same choice. U equals x cubed plus 1, du equals 3x squared. 1/3 du equals x squared dx. And I'm going to rewrite this as the same thing, right? I'm going to say it's going to be 1/3 du square root of u, or u to the 1/2. But now look what I'm going to do. I'm going to change my limits of integration. So in the previous problem, my limits of integration were x equals 0 to x equals 2. Well, if we're making the choice that u is equal to x cubed plus 1, then if x equals 0, u is going to equal 0 cubed plus 1, just 1. And if x equals 2, u is going to equal 2 cubed plus 1, which is 9. So I'm going to actually change the limits of integration to be from 1 to 9. Now, if you do that this way, which I tend to prefer, you don't change back. So I'm going to do the antiderivative of u to the 1/2, which is going to give me 1/3 times u to the 3/2 times 2/3 from 1 to 9. And then I'm literally just going to plug in u equals 9 and u equals 1, instead of going back and plugging in x equals 0 and x equals 2. So we're going to end up getting 2/9 times, if I plug in 9, I get 9 to the 3/2 minus 2/9 times, if I plug in 1, I get 1 to the 3/2. And look, it's exactly the same, right? This part here and this part here are the same thing. They look a tiny bit different, but it's literally the same result. So you can do this U substitution for a definite integral kind of either way. I definitely think it's nicer to change the limits of integration, but there are times when it makes sense to not do that. So it's kind of either way, it's fine, but it takes practice, I guess I should be saying. Let's see. So, oh yeah, I just saw that too. I've got things up there. So I suppose we've circled around it long enough that we should probably talk about the fundamental theorem of calculus, because I can't keep saying things that are definite integrals without having mentioned it. This is definitely something everyone's going to see. So even if you haven't gotten there yet, it's coming up very soon in the future. It's section 5.4. So I don't know what section are people in right now, or do you know? No, okay, that's also fine. It's definitely coming up. I'm not like showing you something that you're not going to have to learn. Definitely going to need to learn the fundamental theorem of calculus. So here's the very, very general idea. So the fundamental theorem of calculus, which is often abbreviated the FTC. Fundamental of calculus. There are actually two parts to it. We're going to focus on the part that's more applicable, which is the part we've just been doing. So here's what the fundamental theorem of calculus says. It says the integral from a to b of f of x dx. And again, the way you should think about this for now is that's the area under the function f of x between x equals a and x equals b. That is equal to f of b, capital F of b minus capital F of a, where capital F of x is the antiderivative of little f of x. This is the fundamental theorem of calculus. It's actually the second part of the fundamental theorem of calculus. Your teacher might also call it the evaluation theorem, because it's literally the way in which we evaluate integrals, definite integrals. So yeah, we did that. Okay, cool. The idea is, for example, if you wanted to, in fact, let's go back and revisit that example we had before, the integral from 1 to 3 of 2x plus 1 times dx, which we showed was equal to 10 in a couple of different ways, right? We did this one before. We know it's equal to 10. But the idea behind this, and this is a little, maybe not quite as detailed as you might see in your class, or you might not. Your teacher might also be kind of hand-wavy about this because there's so many other things to do. But the idea here is that you're taking the curve, taking the area under it from your left endpoint to your right endpoint. And, excuse me, what we're essentially doing is we're adding up a bunch of little rectangles. That's kind of the very idea here, is that we're saying, well, I'm going to draw a bunch of rectangles in here. And each of these rectangles, so we're really adding up a bunch of rectangles. The height of each rectangle is the function height, f of x. And the base of each rectangle, or the width if you prefer, sorry, my trying to write fast, I'm losing letters here, is dx. So we're thinking about this triangle, this rectangle that's over at x has a base of dx, right? The small change in x, and it has a height of whatever your function value is at that point. And so we're saying, okay, we're taking this one rectangle whose base is dx, whose height is f of x, and then we're adding them all up. And that's what this integral symbol kind of means, is you're actually adding up all these rectangles where you're letting the width of each rectangle get smaller and smaller and smaller and smaller and smaller. It's kind of, so there is a more mathematically precise way of talking about it, but it's usually something that gets kind of glossed over in this class. So if we want to talk about, like if you guys find yourself talking about like a limit of a sum, let me know. But usually people are kind of like, this is how we do it. We take the integral, we antidifferentiate, and that's what we get. And we definitely saw an example here, right, where it totally works, right? We did the integral, and we also did it using geometry. Now, the thing about this is it works for shapes that we can't find geometrically. So for example, we could totally find the area under y equal to 9 minus x squared between x equal to 0 and x equal to 3. And it's a good practice just to actually write this out as an integral. So if I'm trying to find the area under the curve, I know I'm doing the integral of that function. And then your lower, unless there's a good reason to write them in some strange order, the lower limit or the left-hand limit should always be the bottom limit of integration, and the upper limit or the right-hand limit should be the top limit of integration. So we should be going from 0 to 3. And the way you want to read this is the integral from 0 to 3. always from the bottom to the top. So it's the integral from 0 to 3 of 9 minus x squared. And what we're calculating here is exactly the area under this parabola. Or that 0.09, I've drawn it very poorly. That 0.30, that point's negative 30. And we're finding this area over here. That's what we're calculating with this definite interval. Okay, now we're going to do it. The antiderivative of 9 is 9x. The antiderivative of x squared is x cubed over 3. We're going to go from 0 to 3. So let's see. If we do that, we're going to get 9 times 3, which is 27, minus 3 cubed, which is also 27 over 3, minus 0 minus 0. So that's going to be 27 minus 9, which is 18. Yeah, let's do another one, just because there's something I really want you to see very, very early on. A lot of the times when your lower limit or your upper limit, when one of your limits of integration is 0, a lot of the times when you plug that in, all the things become 0. Not always. So I want to really, really, really emphasize, stress, say all the words that mean all the things. Don't just assume when you plug in 0, you get 0. Here's an example. Let's say I want to find the integral from 0 to, from 0 to 2 of e to the x plus x squared dx. I don't know what that looks like. I know it looks like some, right? I don't know. I could kind of try to draw it. I know if I plug in 0, e to the 0 is 1. 0 squared is 0, so I get 1. And then when I plug in 2, e squared is like close to 8. It's like 7.8 something, I think. So I get 8 plus 4, 12-ish. So when I plug in 2, I'm getting kind of very large up here, 12. So it's probably doing something, I don't know, like that. I don't really know. I'm just making it up. But that's the area I'm trying to calculate. Okay, so let's do it. So I'm going to anti-differentiate this function. I'm going to get e to the x plus x cubed over 3 from 0 to 2. When I plug in 2, I get e squared plus 2 cubed over 3. Minus when I plug in 0, I don't just get 0, right? I get e to the 0 plus 0. And e to the 0 is 1. So simplifying this a tiny bit, I'm getting e squared plus 8/3 minus 1. I would probably leave this as e squared plus 5/3. That's the simplest way I can write the answer. You should not get a decimal approximation. That's not what they want. This is the best, most accurate, correct way of writing the answer. Not approximately equal to 7.8 plus 5/3, whatever that would be. So definitely leave your answers with all the irrational numbers as is. We don't want to get decimal approximations unless specifically asked for. Let's see here. Yeah. Something else. So what if instead we asked for this? The integral from 0 to 4 of x squared minus 16. Let's just do it and then talk about what the results mean. So let's see. I'm going to get x cubed over 3 minus 16x. Again, I don't need the plus c because it's definite, right? And they would cancel out from 0 to 4. Okay, so let's see. I'm going to plug in 4. I'm going to get 4 cubed over 3 minus 16 times 4 minus 0 minus 0. So 4 cubed is 64 over 3 minus 64. So there's an easy way to do this subtraction. If you see a fraction and a number where they both have the same sort of numerator or this numbers, right? Like you could think of this as 64 over 1. You could totally factor out a 64. Right? I really, really don't want to multiply this by 3 over 3. Because 64 times 3 is not like a super easy thing to calculate. But if I factor out a 64, what am I left with? 1/3 minus 1. And that's something I'm pretty good at doing, right? 1/3 minus 1 is not that bad. 64 thirds minus 64 is 64 thirds minus like 190. Right? I don't want to do 192 thirds. It's just like dumb. So if you see something you can factor out like this, it's usually a good idea to do so. So that's going to be 64 times 1/3 minus 3/3, which is 64 times 1/3 minus 3/3 is negative 2/3, which is going to be negative 128 thirds, which is correct. Why is it negative? Right, if we're talking about area under the curve, that seems weird that it would be negative. Well, not really if we think about what the picture looks like. So I'm going to try and draw a somewhat nicer picture. So this parabola, x squared minus 16, is a regular parabola shifted down 16. So it's got a y-intercept at 0, negative 16, and it's got x-intercepts at plus or minus 4. So what I'm actually doing here is I'm finding this area, but the problem is that area is under the x-axis. And so if you have a curve that's under the x-axis, the area ends up getting counted as negative. If I actually wanted to find, if I wanted to calculate, the area between this curve, or I should say, if I want to calculate the area shaded to the left, shaded over there. So I should say, when you're calculating area, like someone says, find the area that's shaded, your answer should be positive, right? Because an area is always a positive value. There's not really such a thing as a negative area. Sometimes we conceptualize it being negative, but really someone says find the area, they mean that thing should be positive. So if I'm actually trying to find the area of this, well, when we're finding the antiderivative to find the area, or I should say when we're finding the area under the curve, I want to find the area here. I'm thinking of my rectangles again. And if I want to find the height of that rectangle, the height of that rectangle is the top function minus the bottom function. And so my height of my rectangle, well, what's the top function? What's the rectangle hitting at the top?
0.
Yeah, that is y equal to 0. And at the bottom, it's y equal to x squared minus 16. So if I actually want to find the area here, my height is going to be 0 minus x squared minus 16. And so if I was trying to find the area, I would be calculating the integral from 0 to 4 still, because I'm going as far left as 0, as far right as 4. But now it would be 0 minus x squared minus 16, which is the same integral I just did, except it's the opposite sign, which makes sense because if I want to calculate the area, it shouldn't be positive 128 thirds. So the gist is that if your function is below the x-axis, you're going to end up getting a value that's a negative value, because you're essentially, when we calculate this area under the curve, it's really what you're actually calculating is the net area under the curve that's above the x-axis. So yeah. The answer to the first question is definitely appropriately negative, right? This integral here is definitely equal to negative 120 thirds. If I said calculate the area between this curve and the x-axis, the answer would be positive. And what I would do to calculate the area would be to say, well, I could either just take this negative number and make it positive, or I could actually say it's the integral of the top function minus the bottom function.
So we have to just take the negative over and make it positive.
Right. And what this kind of is alluding towards is something where we might like say, find, oh, question, yeah. Sure. This is definite.
So if it's a definite
Right. So if someone asks you for an area, your answer should end up being positive. If someone's asking you for an integral, your answer can be positive and negative. It can also be 0. Yeah.
If you were to write the first thing that you did as an ultimate function, would that be wrong?
That, yes, that would be wrong. So this whole first thing I wrote is correct as is and would be wrong any other way. So let's look at a couple more things. So if I wanted to say find the integral from 0 to pi of cosine of x. Let's see what happens. So antiderivative cosine is, oh, it's always a tough one. Is it positive or negative? How would be the derivative of cosine? Definitely positive sign. Right, because what's the derivative of sine? Cosine. So the antiderivative of cosine is sine. And then we're evaluating this from 0 to pi. Okay, so when I plug in pi, I get sine of pi. And when I plug in 0, I get sine of 0. And sine of pi is 0. And sine of 0 is 0. So we get 0 area. Doesn't seem right. Right? Because I mean, if you think about the cosine function, there's definitely not 0 area under it. Right? It's not like it's not just like the function y equals 0. That would have 0 area under it. But what's happening here is if you graph this, and it really is good to think about the graphs of these things. Cosine starts at 1 and then hits 0 when you get to pi over 2, and then negative when you get down to pi, and then back to 0, and so on. So the cosine function looks like this. And if we're just looking at the area from 0 to pi, this area here is getting counted as positive. This area here is getting counted as negative. And they're totally canceling each other out. That's exactly why we're getting 0 here. Because so what I should really say here is that this is calculating the net area under the curve and above the x-axis. Well, the net amount of area that's above the curve, below the curve and still above the x-axis is exactly 0, because there's the same amount above that's below the x-axis, and so they end up canceling each other out. On the other hand, if someone said differently, calculate the area between y equal to cosine of x and the x-axis, then we need to calculate these two things separately and add them together. So we want to calculate this. So that'd be the integral from 0 to pi over 2 of cosine of x. Right? Because we want the top function minus the bottom function. And then we'd have to add on the integral from pi over 2 to pi of essentially the reverse subtraction. Top function minus bottom function is 0 minus cosine of x. So I should be very, very specific / general at the same time. Meaning, when you're finding the area between two curves, it's always going to be the integral of the top function minus the bottom function. So for this piece here, the top function is cosine, the bottom function is 0. For this piece here, the top function is 0, the bottom function is cosine. And we should have, we'll have time for one more. Yeah, it's tight. I hate this clock right here. It's the worst. Like it's about almost the same time, except it's 2 hours ahead, except it's not really, because it says 12:15 and the time is actually like 12:18. So really, I don't have the 5 minutes I think I have. Anyway, so it's gonna be sine x from 0 to pi over 2 plus negative sine of x from pi over 2 to pi. And when I plug in, I'm going to get sine of pi over 2 minus sine of 0 plus negative sine of pi
minus negative sine of pi over 2. Sine of 0 is still 0. Sine of pi is still 0. So I end up with sine of pi over 2, which is 1, plus negative sine of pi over 2, which is also 1, which is 2. So the area between, sorry, you guys can't see that over there, apologies. The area between the cosine curve and the x-axis is actually 2. Or I should say, the area between the two from 0 to pi is 1 plus 1, which is 2. It's kind of interesting. Well, so there are two different things. The first thing we calculated was just the integral. And the integral gives you the net area. So it counts all the stuff that's above the x-axis as positive. It counts all the stuff that's below the x-axis as negative. It adds them together. And in this case, since they balance each other out, we get 0. Whereas in the second question, I said, I want to actually know how much area is in between this curve and this curve. So I actually have to count each area as positive. Let me just, I know it's like 1 more minute. Let me throw one more thing at you. So let's say we wanted to find the area between the curves y equal to x squared and y equal to 3x, which looks like this. So the way you would do this is you'd say, oh, I need to quote unquote add up all my rectangles. The area of that rectangle, well, it's going to be height times base. The base is dx. It's your small little width of your rectangle, a small change in x. That's what dx is, small change in x. The height is the top minus the bottom, which is going to be 3x minus x squared. So the area would be the integral of 3x minus x squared dx. From as far left as where? How far left do my rectangles go? Or where do these two functions intersect? Well, if I set x squared equal to 3x, bring everything over to the left, I factor out an x. I'm as far left as x equal to 0, and as far right as x equal to 3. So that's how you calculate the area between these two curves. You do the integral of the top curve minus the bottom curve, and then you would go from the left place of intersection to the right place of intersection. We will talk more about this on Thursday, but I wanted to kind of give you one last example there real quick. So you can calculate that on your own. I will stop talking.